In this video, we'll learn how to use quantitative analysis in order to determine the empirical formula of a compound. The key to understanding how that works is to know that when the hydrocarbon undergoes combustion, the products in that reaction are carbon dioxide and water vapor. Because we get one molecule of carbon dioxide for every carbon atom in the hydrocarbon, we can write a mole ratio for that. We say that there's 1 mole of carbon in our compound, our unknown compound, for every mole of carbon dioxide that is produced in the combustion. Because there are 2 hydrogen atoms in a water molecule, there are 2 moles of hydrogen in our compound for every mole of water that's produced in the combustion. So let's turn our attention to what we're actually being asked for in the question. We see that the question is asking us for the molecular formula of this unknown hydrocarbon. We know from previous units that we can get the molecular formula of a compound provided we have its empirical formula and its molar mass. We also see that the molar mass was determined in a separate experiment and the molar mass is given in the problem. So this means that we're going to use the information in the problem and our mole ratios from the combustion of a hydrocarbon in order to determine how many moles of carbon and how many moles of hydrogen are in the unknown compound. Let's begin with the carbon. We're told that in the combustion 3.447 grams of carbon dioxide are produced. We know in stoichiometry that we need to use the mole ratio, so the first step has to be to turn our grams of carbon dioxide into moles, which we can do using the molar mass. 44.01 grams of carbon dioxide per mole of carbon dioxide. Now we can use the mole ratio that we just discussed, which tells us that for every mole of carbon dioxide formed, there must be 1 mole of carbon in the unknown hydrocarbon. Checking to make sure our units are working for us, we have grams of carbon dioxide canceling, moles of carbon dioxide. We're left with moles of carbon, which is good because that's what we're asked for. That's what we're after. And when we put this in the calculator, we see that we get 0.07832 moles of carbon. Now we do the same for the water. We see that in the combustion, 1.647 grams of water are produced. Of course, we are going to use a mole ratio, so the first step is to put that into moles. And then again, we can use the mole ratio that we just discussed that we get from the combustion reaction. And that is that there are 2 moles of hydrogen for every 1 mole of water. Again, making sure that our units are working for us. We have grams of water cancel, moles of water cancel. We're left with moles of hydrogen, which is what we're after, so that's good. We put that into the calculator and we see that there are 0.1828 moles of hydrogen. Since we need the ratio of the number of moles of carbon and hydrogen in a whole number ratio, we'll go ahead and divide both of these numbers by the smaller one, which of course is 0.07832 moles. And that gives us, for carbon, 1 mole of carbon, and for hydrogen, 2.33. But remember, the subscripts in an empirical formula need to be whole numbers. We recognize 0.33 as the decimal form of 1/3, So we'll go ahead and multiply both of these numbers by 3 so that we get whole numbers. And that will give us 3 carbons, and it will give us 7 hydrogens. This means that our empirical formula is C3H7. But we weren't asked for the empirical formula, we were asked for the molecular formula. So to get the molecular formula, we take the molecular formula molar mass, and we divide it by the empirical formula molar mass. The molecular formula molar mass was given in the problem, 86.2 grams per mole. The empirical formula molar mass, I get by adding up the molar masses of my 3 carbons and my 7 hydrogens. So 3 carbons, that'll be 36. 7 hydrogens will be 7. So that gives me an empirical formula molar mass of 43 grams per mole. And putting this into the calculator, we see that this gives us the number 2. This means that to get our molecular formula, we need to multiply all of the subscripts in our empirical formula by 2. Our molecular formula is then C6H14.